Okay, before I get into proving that this function is continuous, it might be worth your while to pause the video and read the text inside the gray box, because it outlines sort of the process that we're going to use to show this in the first place. Okay, so if I try and apply that recipe to do the proof, then the first thing we have to do is to choose our x naught in S, and then we have to let epsilon be bigger than 0. Then we let delta equal, sorry, that's nasty, we let delta equal to something that I'm going to eventually come back to later and fill in. And the reason that I do that is because I want you to see exactly how I derive this delta. Once I get the delta, then the proof is pretty much completed. Okay, so as in the gray box, choose your x in S. And now we're going to just make our key assumption here, that x and x naught are at most delta apart. Okay, so let's just start as we normally would by computing this difference here. If you do this, you will get, so x squared minus x naught squared is actually going to factor as a difference of squares. And the reason that this is nice is because we see this term appearing here, this factor. And we have our assumption about this factor, that this is at most delta. The only problem is now we don't exactly have a bound here. Remember that we want this entire product to be at most epsilon. And so what we need to do in order to bound the product is that we need to bound each of these factors in turn. So the problem here just simply boils down to getting a bound on this second factor, x plus x naught. Well, remember the assumption that x minus x naught is at most delta. Well, this was true for all delta bigger than 0, right? So in particular, I can take delta to be at most 1. If I do that, then that tells me that this difference here is at most 1 itself. And this is sort of a nice assumption to have now, because then we can see that this implies the following, right? And from here, I can get an upper bound on x. And if I get an upper bound on x, this is very nice to have now, because I can go back up here and look at this factor more carefully. Well, you'll notice that because I'm considering x and x naught both in S, that means that they're each positive, right? So both x is positive and x naught is positive. And if they're both positive, I can just do away with this absolute value sign. So this is equal to this, which, as we know from here, x is bounded by 1 plus x naught. So this term is at most 1 plus 2 times x naught. And so essentially we have found a bound on this guy. This is at most 1 plus 2 times x naught. Great. Okay, so now we can put all of this together, and we can say that, well, f of x minus f of x naught is equal to this difference of squares, which I showed you up above. And of course now each of these factors is bounded. So the first one is bounded by our assumption, which is that it's bounded by delta. The second one follows from what we did above, and it's bounded by 1 plus 2 x naught. And remember that this has to equal epsilon. So that tells me that delta has to equal epsilon over 1 plus 2 times x0. Well, okay, great. So basically I found a delta here that's going to work for this proof, right? And so now I can go back up to the very top where I left delta blank and simply fill that in. Except I have to remember one little thing. That is the assumption that I made about delta to begin with, right here. Because this assumption is what led to this conclusion here. I can't have this conclusion without this assumption. So I have to be a little bit more careful and sort of give credit to that assumption. And the way I do that is by taking the minimum of both of these values. Right? Okay, and so that's it. That's really all that I wanted to show you, is how to get this delta value for which this proof works.